Now, we will close the discussion of crack growth with a example that summarizes all of the ideas that we have discussed. And it's a rather nice example. It's based on our classical setup of fracture, the most fundamental one. So therefore, I should emphasize almost everything that I will write through the solution of this example should be stuff that we should know by heart. Okay, so we have a plate with a central crack, not necessarily small. It is a through thickness crack. If it were not through thickness, penny shaped, I have equations for it as well, but it is a through thickness crack, classical scenario of initial size AI. Half the width is AI. The half the width is B for the plate, and we are pulling on this plate. It's a tensile loading, which is mode 1, and there is a thickness which is 6 millimeters. The initial crack size is provided as 1 millimeters, and the width of this plate is 38 millimeters. Okay. And the material is given, so that's all that's eventually going to be given. So we would, of course, be expected to find relevant material tables from the book and make use of them to help us solve the problem. But I'm going to provide you with those parameters. So in particular, the yield strength of AISI 4340 steel is quite high. The fracture toughness, let me just write 1 there. It is mode 1. I don't have to. We've only considered mode 1 so far. Of course, cracks do not grow only in mode 1, but that's what we've looked at as a special case. Remember, we're choosing a path through the complications of mechanics of materials in the context of this course to give you a glimpse into various critical topics. So we have to make a choice at some point, and here we've only looked at mode 1. So the maximum value of the load is 240 kilonewtons. The minimum value is 80 kilonewtons. So its cyclic crack growth will certainly be a problem. And the question first is, what is the failure crack size AF? Okay, now the question does not need to explain further than that, but you will see we will decide the size of the crack depending on whether fracture or yielding happens first. Okay, and remember the idea of the transition crack size. So that's something we could be using, or the analysis that I will do is something we could be using. But we have an idea that one or the other can be more critical first. So yield or fracture is really the underlying question here. Now the second question is, because we have a cyclic load, we are interested in the number of cycles to failure. So in other words, NIF. So the number of cycles to failure will be the number of cycles it takes for the crack to grow from the initial value to the final value, which I don't know yet. But as soon as I determine it through my life estimate, I can find what the corresponding number of cycles is. And then there is the third part, which is also quite nice. Let's first write it, and then we will discuss it as we solve the problem. So we're going to imagine that we have a scenario where the crack is, or the structure is deemed to be free of any crack. But simultaneously, of course, I need to remember that even if there is no crack, I cannot detect one. I need to assume that the cracks that are smaller than the minimum detectable crack size are actually somewhere in the structure. And I will be provided with the fact that for the context of this example, the detectable crack size, minimum one, is actually the initial one. Okay, so AI is simultaneously going to be the detectable crack size for the purposes of part C. So the expected cycle then is n $150,000. Okay, I expect the structure to go through 150,000 cycles with a safety factor of and this factor is on life. Remember, it does matter what it is on. So here it's on life. The safety factor is 3. Okay, so again, let me write down what I've already said. The minimum, the initial crack size is simultaneously, or AI, the value of AI is the detectable crack size. So it's 1 millimeter. Although there is no crack, I need to assume that there is an initial crack size of that size. So if that's the case, are inspections needed? And if yes, when are they needed? Okay, that's the part D, C, and then finally there is part D. Suppose you could detect cracks of size less than 1 millimeter. And the question is, how small a crack should you be able to detect so that you can ensure a service with, or a application with absolutely no inspection? You can be free, you can be sure that essentially you are not going to have any fracture problems. So what is, if AD less than 1 millimeter can be detected, what is an AI? Okay, so the minimum detectable crack size, my instrument can be more sensitive than the initial crack size, but I need to check and make sure that there are no cracks larger than a certain value. So the question asks, what crack size do I need to ensure does not exist so that I can essentially carry out the application without any inspections. Okay, so that's the question. Okay. I will explain the individual parts once again as we solve this problem. Now, let us start with the first part. Now, the first part is asking us to determine what the final crack size is. In other words, what's the size of the crack that is critical to my application? And I see two parameters here, the yield strength and the fracture toughness. So the crack will grow over time and eventually it will reach a value at which first yielding or fracture might happen. Whichever happens first will be the critical value of the crack size, which I will deem to be the failure crack size, the final value, AF. So first I will go ahead and I will calculate the maximum average stress at the cross section. At the cross section where the crack is present. Okay, and because I'm looking at yielding and because the crack size may not be small, I'm going to take into account the presence of the crack. We solved an example some time ago where we did not take into account the area reduction due to the presence of the crack because the crack was much smaller than B and that reduction was negligible. In this case, it will be significant and therefore I'm going to go ahead and take that into account. So I'm going to calculate the max stress at the cross section where the crack is present, and that is going to be equal to the maximum load Pmax divided by the area that is at that cross section reduced by the presence of the crack. Remember, we're just looking at the average stress. So for sure, locally there will be yielding, but with respect to the yield criterion, we're interested in the yielding of the whole cross section. Okay. Now, this is the maximum average stress at the cross section where the crack is present. Area is reduced by the presence of the crack. And if the crack is large enough, then failure will occur through yielding. The value of A at which that happens, I will indicate with A naught. Okay, so now therefore, I know P max 250 kilonewtons. I know all the parameters here, including sigma naught. The only thing I don't know is A naught. So from that equation, I can solve for A naught, and it will come out to be 22.1 millimeters. Okay, so that is, as the crack grows, if it reaches this size, if it reaches it, then yielding will occur in an average manner at the cross section where the crack is present. Not here, not there, at the cross section where the crack is present. So next we look at, right, so this is like the first concern that we have. The second concern that we have, so we've checked for yielding, now we're going to check for fracture. And the way we're going to do that is we are going to calculate the critical crack size. The critical crack size is the size at which the mode 1 stress intensity factor, which is equal to F times S root pi A, is equal to the fracture toughness of the material. That is the definition of the critical crack size. Which stress should I be using? As I do that, I should be using the highest stress that I encounter. So I need to employ S max. Okay. Now, the definition of S max, remember, is equal to the is equal to P max, is a tensile load, maximum stress, tensile stress at the cross section where the crack is present, omitting the presence of the crack. So it is, in these cases, always equal to 2BT, that's the area which divides P max. So here, material parameter is known. I don't know F, I know S max, I will try to solve for AC. Now, the first thing we will do is our classical assumption, which assumes that alpha is much less than 1, or it doesn't even have to be much less than 1. It is less than the 10% error limit on K1. So in this case, that limit, remember, for alpha is 0.4. So if alpha is less than that, I can assume that F is equal to 1. That's the value of F at alpha equals 0 for this particular case. I can omit F and immediately solve for the value of the critical crack size. So that's the nice thing about the 10% limit approximation, remember. And I will get 19.4 millimeters. Okay? Are we okay? Is a question. Think about it for a second. Am I done? Well, if you pause the video for a few seconds, the answer should be no, I'm not done, because I made an assumption and I need to check whether my assumption was satisfied or not. Now, it turns out in this particular case that AC over B is equal to, so 19.4 divided by 38, you can already see that it is less than 0. It's larger than 0.51, and it's larger than 0.5, so 0.5 would be if this were 19 versus 38. It's 0.51, which is larger than 0.4, and therefore I'm not done. My assumption is violated, so I have gone beyond the 10% limit on K1, and I don't know how far I've gone, because F can be decreasing and is increasing very rapidly. It can be increasing by a certain amount and it's increasing very rapidly. I don't know how safe I am. So what I need to do is I need to really solve for the exact value of F. Now, if you do that, then the exact value, so I will say iterate, so numerical algorithm that, or calculator or computer that iterates towards the exact value, will find that AC is approximately equal to 15.88 millimeters, which is actually quite different than 19.4. At this value of AC, F comes out to me, interestingly, very close to the 10% bound. Okay, but that's not something that disturbs us. The 10% approximation takes F to be 1 and predicts that. The actual value, it turns out, corresponds to F equals 1.1, and with that, the value of AC comes out to be 15.88. So that's the final result. Now, from all of that analysis, the only thing that presently concerns us is the fact that AC, the final crack size that causes brittle fracture, is less than A0, the size of the crack that causes yielding. In other words, the result of our analysis says that AF is equal to the critical crack size for fracture, which is 15.88 millimeters, because fracture happens first. Okay? So, but the rest of the analysis really does not depend on whether AF or AC or A0 happens first. What just matters is I identify the correct value of the final crack size for failure, and we've done that. Okay, so that takes us through part A. So now I know the final crack size, and now I can try to estimate the number of cycles that it takes for the crack to grow from this initial size to this failure value, which I now know to be the critical crack size. Okay, so let us do that. So I am not going to go ahead and drive the life estimate once again, but just again, let me emphasize, you are expected to be comfortably derive that equation if needed. And our equation said that if the values of the constants that appear, the parameters that appear in the prototypical form, the ideal form of the Paris equation, are indeed constants, a constant C, F if it's a constant, and it's not, I know, neither is C in general, then I can write the life estimate as follows. For M is not equal to 2. That's our life estimate. Okay. Now, let's get one thing out of the way. F. And the way we're going to look at this is very pragmatic. It's not a big deal. What I'm about to do is give you the sort of argument that we find in the book. Okay, it's a back of the envelope calculation. So what we know presently is, that's why I told you the value of F. It starts with 1 when the crack is very small, or is very, very close to 1, and it grows to 1.1 at the critical crack size AC. Okay. So now the change is very small. You might, if you want, wish to be conservative and take the larger value of F and put it in there. But alternatively, you can do the following, which is suggested in the book. I just remember that the crack growth looks as such. So the rate increases very rapidly. So initially, the value of AI, it's over here. And finally, it goes to AC, okay? And here the value of F, if you like, is 1.1. Here the value of F is 1. And I cut it through and look at 1.05. That's the midway. And I cut it through the midway, and I put a line here and put that line over there as well. And I see that the crack sort of spends more time with values of F that are less than 1.05, and less time with values of F that are larger than 1.05. Since this equation corresponds to some integration over life, if I take 1.05 even, it would be reasonable. It would be like an average value of F. But if I really want to average, I can also take into account that it spends more time being less than 1.05. So I will pick a value that is even less than 1.05. I'm going to take it to be 1.03. Okay, well, why not 1.04? That's also fine, but the point is the midway is 1.05. The crack spends more time in the region that is closer, that is less than this midway value, and so you take a value that is less than the midway value. In this case, I took it to be 1.03. So we're going to take f to be that value. Now, the value of delta S is already provided to us through the values of the stresses. So remember, I already calculated the gross stress. I said that it's P divided by 2BT for these types of problems. So now I'm looking at delta S. So we need to remember and understand what that means. It's the stress range. So it's the load range divided by the area, and that's delta S. And if you calculate that, you will find that it's 351 MPa. So that's also out of the way. So the next thing that we need is the material data. Now remember, we are looking at a scenario where the crack grows from the initial size to a final size, which has to do with fracture. So we're going into the high-end regime towards the fracture, where we know that the rate of the growth of the crack rapidly increases. It's not in the log-log plot scale linear anymore, like Paris suggests. So we should really be using Foreman. But in this case, it turns out we don't have data available for Foreman. We have only data available for Walker. So we're going to be able to make a prediction and hope that it is valid within the safety factor. We're going to be able to make a prediction through Walker only. So data available for Walker. Although Foreman makes more sense, so let me note here that we just don't have Foreman in this case. Okay, a cross for Foreman. Foreman says that the value of C is actually a constant for Foreman. It is C naught divided by (1 minus R to the power M1 minus gamma). Okay. So it is a constant because M, gamma, R will be given, and C naught is also a parameter. So I just need these values now. So first of all, we should notice that the load profile is determined by delta S and R, or S min and S max. In this case, we're using delta S and R. So I know delta S, I just need to find R. So R is equal to S min over S max, but the area is the same for both, of course, so it's equal to P max over P min. Usually, the stress ratio corresponds to the ratio of the max and min and max associated with the loading parameter directly. It could be a tensile load. If it were a bending problem, it would eventually be the ratio of the bending moments, min and max values directly. So P min over P max, in this case, one of them is 80, the other one is 240, so it is equal to 1 over 3. So R is out of the way. That's not a material parameter. The rest are. So gamma, it depends on the material, but also the type of loading is 0.42. M is, so these you have to read eventually from the table where you make your choices. M is 3.24. As I said, it's usually not equal to 2. It's not equal to 2. Now I'm going to write C naught in red so that you are careful about C naught. The value of C naught is equal to 5.11 times 10 to the minus 10. And I'll write the units here. It is millimeters per cycle. Okay, remember, crack growth rate is usually given in terms of millimeters per cycle. So C naught is a parameter that goes into the crack growth rate, but it's not crack growth rate units by itself for C naught. To be consistent with the equation, that the units it has is MPa square root meters to, let me write this explicitly, M. This M is this M. Okay, it's not meters. because there is an exponent m that appears here. That's where that m ultimately comes from. Okay, so the tricky point here is that the stress is MPa. The usual units for stress intensity factor is MPa square root meters. But I have, although everything is in meters, here I have millimeters. So you always have to, in a first step, make sure that you take this value of C naught and convert it, before doing anything else, this is a typical mistake, to meters per cycle, so that everything else that I will be doing will be consistent with the rest of the units. Okay, here I have meters, there I have meters. Eventually everything will work out fine. That m is 3.24. Okay, all right, so that I've done. So with that I can finally determine the value of C. So I'll use the value of C naught and everything else, and I will find that C is equal to 1.095 times 10 to the minus 12 meters per cycle. It has the same units as C naught, everything else is unitless. MPa square root meters to the power n. And I'm just going to again write that m in green so that you don't confuse it with meters. Okay. Good. So now we've done everything. I know everything I need to. Material parameters, of course, there's nothing to memorize about that. Depends on the material, we just look up. But now I can go ahead and plug in the values of everything that I have determined. AI is given. It was 1 millimeter converted to meters, 0.001 meter. Everything should be in meters, right? The exponents and so on and so forth are in terms of those. So the final crack size is the critical crack size that I have determined in the previous sub-question, and therefore I know the value of NIF, and the value of NIF is equal to 77,600 cycles. Okay, great. So we're done with the first two parts. And now let me at this point just pull up the question over here underneath and remind you the rest of the question. So what is the failure crack size? We've determined that. How many cycles does it take to reach it? We've determined that. Now it says, suppose you do an instrumentation, you do a check of the structure, and you say that, well, there is no crack, but your resolution is 1 millimeter, so you have to assume that that crack size of 1 millimeter must exist. That's your resolution. So how many do I need to do inspections to reach this number of cycles with that safety factor? So we provided the minimum detectable crack size as 1 millimeter because we've already done an analysis in part B based on that. So we want to make use of it. Okay, so we're going to base our argument based on the result that we have just determined, which is the fact that number of cycles it takes for the crack to grow to the final value is 77,600. Now, the expected cycle is 150,000 cycles, and we want a safety factor of 3. The question is, do we need inspections and when? So think about that for a second by pausing the video. Okay, so now, do we need inspections? Well, we certainly need inspections because the number of cycles to failure is this, which is less than the expected cycle. You see, there is a safety factor on life. If I really don't want to do anything, even if this is 1, I expect to be able to reach 150,000 if I don't want to do inspections, but I will fail at 77,600. So certainly we will need inspections. So part C, therefore, is something we can immediately deduce. NIF is less than N0, okay? And therefore, we immediately will have failure if we don't do any surface. So now we have a safety factor. So now when we apply the safety factor, we know that we will reach failure after this many cycles, so my safety factor will apply here. So my surface safety factor is going to go on top of this value for number of cycles to failure. So when I write the safety factor on life, which is a determination going to allow me to determine when I do service, the safety factor comes through not N0, but rather from NIF, because that is going to give me failure. That's my safety factor. That's therefore when I should do service. So NIF is 77,600. The safety factor is 3. So the service, the life for service is 25,000, approximately, let's say, 900 cycles. So that's when you do your cycle, your service. Now remember, we want to go up to 150,000 cycles. So it seems that the only way you can do it is you cycle it, let's say at roughly 25,000, and then you cycle it, you service it again at 50,000 cycles, a total number of 50,000, 75,000, 100,000, 125,000. Then once you do that, you do your service 1, 2, 3, 4, 5 times, then you can reach that value of 150,000. So you have to do a number of services regularly at so many intervals so that you can reach the final life that you expect to reach. Okay? And this is the typical scenario when you work with structures such as, for instance, aircraft. Okay, so the last part, let me also remind you that by slipping up the question over here. Now, suppose you don't want to do any inspections because inspections take time, you have to take the structure out of service, you lose money, whatever. So suppose I could build a better instrument, and this instrument can detect crack sizes of less than 1 millimeter. Because I know that if I can detect the smallest value as 1 millimeter, then I'm doomed. I have to do inspections very regularly. So I need to detect something that is much less. And suppose I can detect a very, very small value, any value. The question is, what is the value, the smallest crack I should find, the largest crack, I should find, okay? Which should certainly be less than 1 millimeter. What is the largest value I should detect so that I will be sure when it grows, it will reach failure to within my safety factor before I have to do any service with this expected cycle with that safety factor. Okay? So think about that answer for a second, how you would do it. We have everything on the papers that we have on our notes that we have developed as we solve this problem. So now the answer is we want NIF, okay, to be 150,000, that's our goal, but with a safety factor of 3, okay? So now we are in a scenario where we do not want any type of failure, and therefore within a safety factor of 3, so I need to make sure for 150,000 with a safety factor of 3, I go up to 450,000 cycles. Okay, so I'm trying to determine this. This is now 150,000. It's not service anymore. It's my target. This is the safety factor, and therefore 450,000 is my goal. Okay. So now the question is, what is the minimum largest crack I should find, or conversely, what should be my minimum detectable crack size so that I don't have to worry about failure. So that means that number of cycles to failure, which is now 2 within a safety factor 450,000, is the number of cycles it takes for the crack to grow from that unknown minimum detectable crack size, which is going to be our new initial crack size, which is certainly going to be less than 1 millimeter according to my analysis. I want to determine that value so that when it grows to the final crack size, and the final crack size is always the critical crack size, that doesn't change. the number of cycles it takes for that to happen is equal to NIF 450,000, where the expression for NIF is this, right? So we have everything that we need to know. AC is given, everything else we've determined. Left-hand side in this case is known, and we're asking the converse question of finding, right, what the initial crack size is, and from this you will find that the detectable crack size should be 0.066 millimeters. Okay, so more than one order of magnitude smaller. One order of magnitude would be 0.1. It's even less than that compared to 1 millimeter. Right? So that is the result of our analysis. Now, how would that help us? Well, the way it would help us is, for instance, well, I would now know that suppose my design or my operation requirements say that, well, I don't want to do any service. That means you have to be able to detect this minimal crack, detectable crack size. You have to ensure that there is no crack that is larger than this value. If your instrument has this resolution, then you have to assume that this value exists. If that's the case, we know our final crack size, so that's what I can ensure. But for instance, suppose it turns out that this value is too small for any instrument you have available. There is no instrument that measures a crack of size less than 0.1 millimeters, let's say, which means therefore that you will have to do service at one point or another. If the guy that operates your design says that, no, I don't want to do any service, what you have to do now is the only thing remaining. You have to change your design so that the loads are smaller and therefore the crack growth rates are smaller, and therefore you can actually reach the desired goal with this resolution of the instrument. So this type of analysis allows us not only to determine service lives, certain requirements on application of your structural design, but also on how you should possibly modify your design.